Our sun may have a twin, a lost sibling hiding in the depths of space. This is not just a poetic idea, it is a serious scientific mystery with a dark and dramatic name, Nemesis. By the end of this journey, you will understand the compelling evidence for a cosmic companion and how its ghostly orbit might hold the key to Earth's most devastating ancient disasters. We are going to piece together a story of stellar birth, galactic archaeology, and a chilling cycle of extinction written in rock and ice. What do you think is the most haunting secret our solar system might be keeping? To find a lost twin, you first need to know its family. Let us look at the sun's birthplace, a scene of incredible violence and beauty. It all begins in the cold, dark depths of space within vast structures called giant molecular clouds. Picture these not as wispy cirrus clouds, but as colossal, light-years-wide mountains of gas and dust, so dense they blot out the light of stars behind them. Within these frigid nurseries, gravity begins its slow, relentless work, pulling together knots of material. A clump collapses, spins, and heats up. When the core temperature reaches millions of degrees, nuclear fusion ignites and a star is born. But a single clump rarely makes just one star. The process is chaotic, like a whirlpool in a cosmic river, often fragmenting to create multiple stars at once. This is how we get stellar families or open clusters where hundreds, sometimes thousands of sibling stars are born together from the same cloud. They are lit by the same first light, swaddled in the same dusty cradle. For a few million years, these young stars blaze together, a glittering family portrait against the dark velvet of space. Our own sun, 4.6 billion years ago, was part of such a family. The evidence for this is overwhelming. When we look at other young star clusters in our galaxy, like the famous Pleiades, we see the blueprint. Almost every star we observe is born with siblings. Statistically, it is far more likely our sun was one of many, not a solitary birth. Over immense stretches of time, the gentle gravitational tides of the galaxy pull these clusters apart. The sibling stars drift away from each other like dandelion seeds scattered by a gentle wind, each embarking on its own solitary journey across the Milky Way. So the question is not if the sun has brothers and sisters out there, but where they are now and if we could ever find one. But among those scattered siblings, one stands apart in the scientific imagination. It is not a nurturing twin. It is a ghost, a dark companion with a name pulled from Greek mythology, Nemesis, the goddess of retribution. In the early 1980s, a pair of paleontologists made a shocking discovery while studying Earth's fossil record. They noticed a pattern, a grim cycle of mass extinction events occurring roughly every 26 to 27 million years. The timing was too precise, too regular to be mere coincidence. Something outside our planet, something on a cosmic clock, seemed to be triggering these periodic cataclysms. This is where the Nemesis hypothesis was born. Scientists proposed that our sun could have a distant, dim companion star, one we have never seen. This would not be a bright sibling like those in the Pleiades, but a failed star, perhaps a faint red dwarf or a cold, dark brown dwarf, a celestial object too small to ignite sustained fusion. Its proposed orbit is the key to the mystery. Imagine a path so elongated it is more like a lopsided ellipse than a circle. For most of its immense journey, Nemesis would be drifting in the frozen darkness far beyond the known planets, perhaps a light year away, nearly in the interstellar void. But then, every 26 million years or so, its orbit swings it back into the inner reaches of our solar system. Its gravitational presence, like a giant hand stirring a pond, would disrupt the icy debris at the solar system's outer edge, a region we call the Oort cloud. This disturbance would send a storm of comets raining inward, a celestial bombardment with Earth directly in the line of fire. So Nemesis is framed not as a lost brother, but as a harbinger, a Death Star whose periodic return might be written into the very bedrock of our planet as a cycle of annihilation and rebirth. The question shifts from a simple search for a sibling to a far more ominous one. Is there a clockwork killer hidden in the dark, ticking down to our world's next potential catastrophe? The fossil record is Earth's autobiography, written in stone and bone. For decades, scientists have read its chapters, chronicling the rise and fall of countless species. But in the 1980s, two paleontologists, David Robb and Jack Sepkoski, were not just reading individual stories, they were analyzing the entire narrative arc. They compiled data on marine life over hundreds of millions of years, and a startling pattern emerged from the chaos. It appeared that major extinction events, where a significant percentage of all life on the planet vanished, were not random tragedies. They seemed to strike with a terrible regularity, roughly every 26 to 27 million years. This was not a subtle rhythm, it was a pulse, a heartbeat of death echoing through deep time. The implications were staggering. If true, it meant these cataclysms were not caused by internal, earthly processes alone, like volcanic eruptions or climate shifts, which would be irregular. Something with clockwork precision, something operating on a timescale far beyond human history, was influencing life's fate. The most famous of these events is the Cretaceous-Paleogene extinction, which occurred around 66 million years ago. We all know the story: a massive asteroid impact, global wildfires, a nuclear winter scenario that ended the reign of the dinosaurs. But within this new framework, that asteroid was not a lone freak accident. It was potentially just one event in a series, a single, devastating tick of a cosmic clock. The dinosaur killer becomes part of a pattern, a chapter in a recurring cycle of bombardment. Think of it like this: if Earth's history were a year, mass extinctions might not be unpredictable storms, but seasonal hurricanes arriving with grim predictability. This cyclical evidence was the spark that ignited the Nemesis hypothesis. Scientists needed a mechanism, a celestial metronome that could trigger a comet shower every 26 million years. The search for a cause led their gaze outward beyond the planets to the darkest and most distant reaches of our own solar system. That grim celestial clock needed a physical mechanism, a way to translate a distant star's orbit into fire and ice on our world. The answer lies in the darkest, most remote territory of our solar system, a place called the Oort cloud. Picture the solar system you know, the Sun and its planets, as a bright, bustling city. The Oort cloud is the vast, silent wilderness that surrounds it, stretching nearly halfway to the next star. It is not a cloud you can see, but a theoretical shell of trillions of icy objects, leftover rubble from the solar system's formation. These are not asteroids, they are pristine cometary nuclei, each a dirty snowball of ice, rock, and frozen gases, some as large as mountains. They orbit in a deep freeze so profound that the Sun is just a particularly bright star in their sky. For billions of years, most of these objects have drifted in a state of gravitational balance, a frozen archive of our system's earliest days. But introduce a massive gravitational disturbance into this delicate equilibrium, and everything changes. This is where Nemesis plays its part. On its proposed elongated orbit, every 26 million years it would make its closest approach to the Sun, diving through the inner Oort cloud. The gravitational pull from this passing star, even at a great distance, would be like a giant hand shaking a tree laden with fruit. It would not need to hit anything directly. Its mere presence would send gravitational ripples through this sea of icy bodies, nudging countless comets out of their stable orbits. Some would be flung out into interstellar space forever, but a significant number would be sent tumbling inward toward the warmth of the inner solar system. This creates a cometary shower, a storm of icy missiles on new, dangerous trajectories. As these displaced comets fall sunward, they cross the paths of the planets. Earth, moving along its own orbit, becomes a moving target in a cosmic shooting gallery. A direct impact from a large comet would be an event of almost unimaginable power, far greater than the asteroid that doomed the dinosaurs. But even a near miss or a cluster of smaller impacts could be catastrophic. The real devastation comes from the aftermath. A major impact would vaporize rock and water, launching billions of tons of dust and soot into the upper atmosphere. This shroud would block sunlight for months or even years, collapsing the food chain at its base through a phenomenon called an impact winter. Global temperatures would plummet, photosynthesis would stop, and ecosystems worldwide would collapse. The fossil record cycle of death finds its proposed physical cause not in a single killer, but in a periodic trigger, a dark companion whose gravitational whisper stirs a sleeping storm of ice at the edge of everything we know. The hunt for this cosmic phantom demanded a new kind of vision. Our eyes, and even our most powerful optical telescopes, are blind to the coldest, dimmest objects in space. A failed star like a brown dwarf emits almost no visible light, having never truly ignited. But it does glow with a faint, residual heat from its violent formation, a warmth detectable as infrared radiation. To find something that hides in shadow, you must look for its heat signature. That was the precise mission of NAS, a wide-field infrared survey explorer, a spacecraft known as WISE. Launched in December 2009, its goal was monumental: to scan the entire sky not once but 1.5 times in 4 different infrared wavelengths. It was a celestial census designed to map the hidden population of the solar neighborhood. The mission scientists were explicitly hunting for cold, distant objects, whether a hypothesized giant planet in the outer solar system, sometimes called Planet X, or something even more significant, a substellar companion. Some researchers gave this hypothetical object another name, Tyche, the Greek goddess of fortune, a more benevolent counterpart to the doom-laden Nemesis. The data from WISE was a treasure trove of cosmic heat maps containing the faint thermal whispers of millions of objects. The promise was intoxicating. Within this vast digital archive, the long-lost twin of our sun, or its dark, diminutive sibling, might finally be waiting to be found. The ghost had a chance to be photographed not by its light, but by the memory of its warmth against the absolute cold of space. The data from WISE was a monumental achievement, a complete infrared map of the cosmos. So, what did it find in our own backyard? The survey was spectacularly successful in one regard. It catalogued thousands of previously unknown brown dwarfs, those cold, failed stars scattered throughout our galactic neighborhood. But when scientists meticulously combed through the data, searching for the specific signature of a substantial companion to our sun, they found only silence. The results were definitive. WISE ruled out the existence of any object with the mass of Saturn or larger within a distance of 10,000 astronomical units. To put that in perspective, 1 astronomical unit is the distance from Earth to the Sun. So, they searched a sphere of space with a radius 10,000 times that vast distance and found nothing of that size. Furthermore, it found no star-sized object, no twin sun, out to about 1.5 light-years. That is a staggering volume of empty space. This was a serious, perhaps fatal, blow to the classic Nemesis hypothesis as originally conceived. The idea of a Jupiter-sized or even a star-sized Death Star on a regular orbit, waiting to be found, was effectively laid to rest by the cold, hard data. The infrared eye saw no giant, no luminous twin. Yet, science rarely deals in absolute endings. Instead, the question evolved: could the companion be smaller, colder, or on an orbit so wildly elongated that it is currently far beyond even WISE's sensitive gaze? The hunt did not stop, it simply changed target. The focus shifted from a giant to a ghost, an object perhaps no larger than Earth, or a supremely cold brown dwarf so faint it slips below even infrared detection. The absence of evidence within a certain range is not evidence of absolute absence. It simply means the mystery, if it exists, is now hiding in a different, even darker corner of the cosmic map. So the classic Nemesis star may be a phantom, but the 26 million year pulse in the fossil record remains a tantalizing, unresolved mystery. If a Death Star is not ticking in the dark, what other cosmic clock could explain it? Astronomers have looked beyond a single companion to consider the immense gravitational rhythms of our entire galaxy. Our solar system is not stationary, it is on a grand journey orbiting the center of the Milky Way. But this orbit is not a simple, flat circle. Think of the galaxy's disk, that brilliant spiral of stars, as having a certain thickness, like a vinyl record. As the Sun travels around the galactic center, it also bobs up and down, weaving through this disk in a slow, vertical oscillation. Picture a horse on a merry-go-round, not just going in a circle, but also gently rising and falling with the rhythm of the ride. This journey takes us through different densities of interstellar gas, dust, and most importantly, the galaxy's own pervasive gravitational field. This is where the galactic tide theory comes in. Just as the Moon's gravity pulls on Earth's oceans to create our daily tides, the combined gravitational pull of all the stars, gas, and dark matter in the Milky Way's disk exerts a gentle but persistent tidal force on our entire solar system. For most of our journey, this force is too weak to matter, but when the Sun reaches the densest part of its vertical oscillation, passing through the crowded mid-plane of the galactic disk, this tidal pull strengthens significantly. Scientists propose that this periodic strengthening, which happens on a timescale remarkably close to 26 to 30 million years, could act like a gentle, rhythmic squeeze on the distant Oort cloud. It would not need a passing star, the galaxy itself becomes the perturber. Each time we dive through the galactic plane, this collective gravity gives the cloud of icy bodies a collective nudge, potentially dislodging comets and sending them inward. It is a clockwork mechanism built into the very architecture of our galaxy, a celestial metronome set by our Sun's eternal dance among the stars. Yet another intriguing possibility brings the mystery closer to home, or at least to the outer frontier of our own planetary family. In recent years, evidence has mounted for the existence of a large, undiscovered planet in the icy darkness far beyond Neptune. This hypothetical world, often called Planet 9, is not the tiny Pluto, but a super-Earth, a rocky giant several times the mass of our own world, tracing an immensely long and tilted orbit. Its gravitational influence is inferred from the peculiar, clustered orbits of small icy bodies in the distant Kuiper belt. If real, Planet 9 would be a major gravitational player in the solar system's outer darkness. Some researchers have asked, could this world, on its own multi-thousand-year orbit, also be responsible for periodic comet showers? The idea is that as Planet 9 swings along its elongated path, its gravity could, over immense timescales, slowly torque and reshape the inner edge of the Oort cloud. Instead of a single, dramatic shake from a passing star every 26 million years, the effect would be more gradual and complex, a slow build-up of gravitational nudges that eventually sends a wave of comets cascading inward. This would not produce a perfect metronome tick like the Nemesis hypothesis, but it could create episodic spikes in comet activity that loosely match the fossil record cycles. Here, the agent of change is not an intruder from interstellar space, but a hidden member of our own solar system, a shepherd world whose distant dance might unknowingly herd icy visitors toward the inner planets. The search continues not for a single killer, but for any gravitational fingerprint that can explain the rhythm of life and death written in Earth's stone. This galactic dance provides a powerful alternative to the stellar intruder. Our solar system's journey is not a flat, circular track around the Milky Way center. Instead, it's a grand, three-dimensional oscillation. Picture the galaxy's brilliant spiral disk not as a flat sheet of paper, but as having a substantial thickness, more like a fluffy pancake or a vinyl record. Our Sun, along with all its planets, does not glide smoothly within this plane. It actually bobs above and below it, riding a wave of gravity in a slow, vertical motion. One complete up and down cycle takes an astonishing 60 to 70 million years. For context, the last time our system was at its current height above the plane, the dinosaurs were just beginning their rise to dominance. We are, in a very real sense, surfing the galaxy on a timescale that dwarfs all of human history. The crucial moment comes when we pass through the densest mid-plane of the galactic disk. This region is crowded with stars, gas clouds, and most importantly, the invisible scaffolding of dark matter. It's the most gravitationally intense part of our vertical journey. As we plunge through this crowded neighborhood, the collective gravitational pull from all that mass, a force astronomers call the galactic tide, strengthens significantly. Think of it like wading into the ocean. Ankle deep, you barely feel the water's push and pull. But as you move into deeper water, the force of the waves becomes impossible to ignore, tugging at your legs with every surge. The galactic tide acts in a similar way on the outermost reaches of our solar system. That distant reservoir of icy comets, the Oort cloud, feels this periodic gravitational squeeze. When the tide is strongest during our passage through the galactic plane, it can give countless comets a collective nudge, destabilizing their orbits and sending a storm of them tumbling inward toward the Sun and potentially toward Earth. The timing here is profoundly compelling, yet not a perfect match. The solar system's vertical oscillation is 60 to 70 million years, but the fossil record suggests extinction pulses every 26 to 27 million years. At first glance, that seems to rule the galactic tide out. However, our journey around the galaxy is more complex than just bobbing up and down. We also encounter spiral arms, regions of even greater density, and other large-scale structures. Some scientists propose that it's the combination of the vertical motion and these other galactic rhythms that could produce a stronger perturbation every 26 million years or so. The tide may not be a single, definitive trigger, but part of a symphony of gravitational influences that occasionally harmonize to create a crescendo of comets. This theory elegantly replaces a single Death Star with the architecture of the galaxy itself. The cosmic clock is not a hidden companion, but the very rhythm of our home in the Milky Way, a pulse so vast we are only now beginning to feel its slow, distant beat. Yet another gravitational player might be hiding within our own solar system's boundaries. While the galactic tide is an external force, the clues pointing to an undiscovered world come from the strange behavior of objects we can already see far beyond Neptune. Astronomers studying the distant Kuiper belt, a ring of icy debris, began noticing something bizarre. A handful of the most distant objects out there, small worlds with orbits taking them hundreds of astronomical units from the Sun, were not scattered randomly. Their elongated paths were strangely aligned, as if herded, clustering in both the orientation of their orbits and the direction of their closest approach to the Sun. This peculiar clustering is statistically extremely unlikely to happen by chance. It is the celestial equivalent of finding several scattered compass needles all pointing in the same specific direction, despite being in different rooms. The most compelling explanation is the gravitational influence of a massive, unseen planet. This hypothetical world, often called Planet 9, is no small ice dwarf. Current models suggest it could be a super-Earth with a mass 5 to 10 times that of our own planet. Its proposed orbit is staggering. It would swing along a path 20 times farther from the Sun than Neptune on average, taking perhaps 10,000 to 20,000 years to complete a single, lonely revolution. For most of that immense journey, it would be a frozen, dark world reflecting only the faintest glimmer of sunlight. So, could this hidden giant be our modern nemesis? Could it, rather than a passing star, be the gravitational architect behind periodic comet showers? The mechanics would be different but equally profound. Planet Nine's immense gravity and tilted orbit would, over millions of years, slowly torque and reshape the inner edge of the scattered disk, a region of icy bodies just outside the Kuiper belt. Think of it not as a sudden shake, but as a steady, relentless push on a cosmic pendulum. Over many orbits, this influence could build up, gradually nudging a population of icy objects until their orbits become unstable. Eventually, a cascade of them could be redirected, sent plunging inward toward the inner solar system. This would not necessarily create a perfect 26 million-year clockwork tick. The effect might be more episodic, creating waves of comet activity that come in clusters over geological time. Intriguingly, some computer simulations suggest that a Planet Nine-like object could indeed generate periods of enhanced comet flux that loosely match the timings in the fossil record. It would not be a Death Star from afar, but a shepherd from within, its distant dance unknowingly guiding icy visitors toward a fateful rendezvous with Earth. The search for this world is now one of astronomy's great quests, a hunt for a ghost written in the orbits of smaller ghosts, a potential key to understanding not just the structure of our solar system, but perhaps the very rhythm of life on our planet. Theories of cosmic clocks and distant shepherds are compelling, but they demand proof written here on Earth. That evidence comes in the form of scars, colossal wounds punched into the planet's crust by visitors from space. These are impact craters, the silent testimony of ancient cataclysms. The most famous is Chicxulub, buried beneath the Yucatan Peninsula in Mexico. This 150-kilometer-wide scar is the smoking gun for the dinosaur extinction 66 million years ago. The rock layers tell a clear story, a thin, global line of iridium-rich clay, an element rare on Earth but common in asteroids and comets, sits directly between the age of dinosaurs and the rise of mammals. Below that line, dinosaur fossils abound. Above it, they vanish. Chicxulub is the monumental period at the end of that sentence, but to test a cycle, you need more than one data point. Scientists have searched for patterns among other massive craters. Intriguingly, some appear in pairs or clusters around the same time, suggesting a period of heavy bombardment. For instance, the Silver Pit crater in the North Sea and the Boltish crater in Ukraine both formed very close to the Chicxulub event, as if Earth was struck by several fragments of a larger, disintegrating comet. Finding and dating these ancient wounds is a monumental detective story. Erosion, tectonic activity, and the slow creep of continents have erased or buried most of them. The older the crater, the harder it is to find. Researchers don't just look for giant holes, they search for shocked quartz, glassy beads called tektites, and those telltale layers of extraterrestrial material settled in the geologic record like dust after a cosmic battle. The quest is to see if these impact layers stack up at regular intervals. Do we find evidence of catastrophe roughly every 26 million years? The answer is tantalizing but messy. Some studies of crater ages have suggested a weak periodicity, a faint heartbeat in the data. Others find the record too incomplete, the dates too uncertain to say for sure. It's like trying to reconstruct a symphony from a handful of scattered, ancient notes. You can sense a possible rhythm, but you can't be certain of the tune. The ground beneath our feet holds the only direct record of these celestial attacks, and we are still learning how to read its most violent chapters. 66 million years is a blink compared to the solar system's deeper history. Long before dinosaurs or even complex life, our young world endured a far more brutal siege. We call it the Late Heavy Bombardment, a period of apocalyptic violence that reshaped the inner solar system roughly 4 billion years ago. This was not a gentle rain of comets, but a sustained, planet-wide artillery barrage from countless asteroids. The evidence is written on the face of our moon. Those vast, dark plains we call Maria are not ancient oceans, but colossal basins of solidified lava that welled up after cataclysmic impact. The Moon, lacking erosion or plate tectonics, preserves this ancient scar tissue perfectly, a pockmarked archive of that primordial hellscape. Earth, being larger and a more attractive target, would have been struck even more frequently. Any early oceans would have boiled, the crust would have melted and reformed, and the very atmosphere might have been stripped away and replaced. This period likely sterilized the planet's surface repeatedly, resetting the clock for life's emergence with every world-shattering impact. What could have caused such a sustained, system-wide cataclysm? The leading theory points to a grand reshuffling of the giant planets. In the solar system's earliest days, Jupiter, Saturn, Uranus, and Neptune may not have orbited where they do today. Their gravitational dances, interacting with a vast disk of leftover planetary building blocks, could have triggered a sudden instability. As the giants migrated to their current orbits, their immense gravity would have hurled a storm of asteroids and comets inward, a cosmic pinball game with the rocky planets as the targets. But here is where our narrative threads might intertwine. Could a stellar sibling have played a role in this ancient chaos? If the Sun was born with a twin, its gravitational presence in those formative years would have been profound. As the sibling stars slowly drifted apart, their parting gravitational pull could have been the very nudge that destabilized the giant planet's orbits, kicking off the migration that led to the bombardment. In this speculative view, the lost twin would not be a periodic bringer of doom like Nemesis, but an architect of the solar system's violent adolescence, a ghost whose early departure set the stage for everything that followed, including the eventual formation of a stable Earth. The late heavy bombardment may be the oldest, most violent chapter in a story that connects the birth of our star family to the evolution of our world. A reminder that the architecture of our cosmic neighborhood was forged in fire and ice. Finding the Sun's lost siblings is a search for ghosts in a crowd of billions. The challenge is not just their distance, but the relentless, slow-motion dissolution of their birthplace. That glittering open cluster where our Sun was born did not stay together. Over hundreds of millions of years, the gentle but persistent gravitational tides of the Milky Way galaxy itself began to pull the family apart. Picture a group of friends setting out on a hike through a vast, rolling landscape. At first, they walk close together, but as the terrain changes hills, valleys, winding paths, they naturally drift apart, some walking faster, some slower, until they are scattered across miles of wilderness, each on their own solitary journey. Galactic tides work in a similar way. The combined gravitational pull from the galaxy's massive central bulge and its sprawling spiral arms exerts a differential force on a star cluster. Stars on the outer edges of the cluster feel a slightly stronger pull than those near the center, and this subtle difference over cosmic time stretches the cluster like taffy. But the tides are not the only force at work. Within the cluster itself, stars are constantly moving, gravitationally nudging each other as they pass. Sometimes these close encounters act like slingshots, giving one star a boost of velocity that flings it right out of the family group forever. This process, called violent relaxation, steadily evaporates the cluster, sending its members streaming away into the general stellar population of the galaxy. After a billion years or so, the cluster is completely dissolved. Its stars, once bound by gravity and birth, become cosmic orphans, indistinguishable from the billions of other stars that fill the galactic disk. This is the fate of nearly all open clusters, and it is almost certainly what happened to our Sun's family. So, if the stars are physically scattered and mixed beyond recognition, how could we ever hope to identify one? This is where a fascinating scientific discipline comes in: galactic archaeology. Just as human archaeologists piece together ancient cultures from pottery shards and buried tools, stellar archaeologists reconstruct the history of stars from the elements they contain. The key is in the chemical fingerprint. Every giant molecular cloud, every stellar nursery, has a slightly unique chemical composition. It is a specific blend of elements forged in earlier generations of stars and supernova, a cosmic recipe. When a cluster of stars forms from that same cloud, they all inherit that exact recipe. They are made from the same stuff. As these stars begin their lives, this chemical signature is locked into their atmospheres, a permanent birth certificate. So, even after 4.6 billion years of wandering alone through the galaxy, our Sun still carries within its light the precise chemical makeup of its original nursery. To find a sibling, astronomers do not just look for stars that look like the Sun in size or temperature. They use powerful spectrographs to break starlight into a rainbow, searching for the faint, telltale absorption lines that reveal the presence and abundance of dozens of different elements: iron, silicon, oxygen, carbon, and rare earth metals. They are looking for a star with a chemical fingerprint that is a perfect match. It is a needle in a haystack search on a galactic scale, but it is the only way to find true family after the great dissolution has run its course. The hope is that somewhere in the vast stellar census of the Milky Way, another star shines with our Sun's exact elemental DNA, a silent testament to a shared beginning in a cloud of dust and light that vanished eons ago. This birth certificate is written not in ink but in light. When astronomers point their most powerful telescopes at a star, they capture more than just a point of brightness. They gather its story. The tool for this cosmic forensics is called high-resolution spectroscopy. It works by splitting the star's light into an exquisitely detailed rainbow, a spectrum. But this is no ordinary rainbow. It is etched with thousands of dark, vertical lines, like a unique barcode. Each line corresponds to a specific element in the star's outer atmosphere, absorbing a tiny fraction of the light at a precise wavelength. The depth and width of these lines tell a profound tale. They reveal not just which elements are present, but their exact abundances. A slightly deeper line for iron here, a distinct pattern for silicon there, a faint signature of europium. All of it combines into a chemical fingerprint as unique as a snowflake. The crucial insight is that stars born from the same primordial cloud share this fingerprint. They are made from the same batch of ingredients cooked in the same stellar nursery. So, to find the Sun's siblings, astronomers are not looking for stars that merely resemble it in color or size. They are conducting a galactic DNA test, searching for that one in a billion star whose spectral barcode is a perfect match to our own. This monumental search required a new kind of map. Enter the Gaia spacecraft and ground-based surveys like the Gaia ISO survey. Gaia's mission is astrometry, measuring the precise positions, distances, and motions of over a billion stars, creating a three-dimensional atlas of our galaxy. But to find family, you need more than just an address, you need a biography. That is where complementary projects step in. The Gaia ISO survey, using the Very Large Telescope in Chile, collects high-resolution spectra for hundreds of thousands of stars that Gaia identifies. It is a massive chemical census tagging each star with its elemental abundances. The goal is to cross-reference the galactic map with the chemical database. Imagine having a list of every person in a country, their current location and their travel history, and then being able to run a DNA test on each one to find your long-lost relatives. The scale is almost incomprehensible, but it is the only way to solve a mystery 4.6 billion years in the making, and then a spark of recognition. Amidst the millions of data points, a few stars have emerged as compelling candidates. One is HD 162,826, a star in the constellation Hercules, about 110 light-years away. Another is HD 186,302 in the constellation Pavo, roughly 180 light-years distant. Analysis shows their chemical compositions are startlingly similar to the Sun's. The match is not just close, it is remarkably precise across a wide range of elements. They are the same age within a few 100 million years, and their motions through the galaxy, when traced backwards, suggest they could have originated from the same region of space. The excitement in the astronomical community was palpable. Have we found them? Are these the sun's long-lost twins? The answer is tantalizing but cautious. They are the best matches we have found so far, strong candidates that passed the first rigorous rounds of the galactic DNA test. Yet, to declare a definitive sibling requires an exact match, and the chemistry, while incredibly similar, shows subtle differences. These differences could be due to the star's individual life experiences after birth, or they might indicate the stars formed from a neighboring cloud in the same giant complex, making them more like cousins from the same stellar neighborhood rather than true twins from the same womb of gas. The hunt continues, refined by each new data release. Every potential match, even a near miss, brings us closer to understanding the crowded nursery our sun once called home. Among the billions of stars in the galaxy, a handful stand out as possible family. These are the stellar candidates, stars whose light carries a chemical signature hauntingly similar to our own sun. The most famous of these is a star catalogued as HD 162,826. You can find it in the constellation Hercules, though it is far too faint to see with the naked eye, lying about 110 light-years away. It is roughly 15% more massive than the Sun and slightly hotter, but when astronomers analyzed its spectrum, they found something remarkable. The abundances of key elements, from iron and silicon to the rare earth elements like europium and yttrium, matched the Sun's own composition with astonishing precision. It is as if you compared two complex recipes and found not just the same ingredients, but in the exact same proportions, adding to the intrigue when scientists used data from the Gaia mission to rewind its motion through the galaxy. Its past trajectory placed it in the same general region of space as our Sun billions of years ago. It is a strong candidate, a star that passes both the chemical and the dynamical tests. Another compelling possibility is HD 186,302, located in the southern constellation of Pavo, roughly 180 light-years distant. This star is even more Sun-like in its mass and temperature, earning it the label of a solar twin. Its chemical fingerprint is also an incredibly close match. The probability of finding two stars with such similar chemistry by pure chance in the vast galactic field is incredibly low. These stars did not just happen to form with the same recipe, they almost certainly inherited it from the same source. So, does this mean we have found the Sun's lost siblings? The answer is more complex than a simple yes. While the chemical similarity is the strongest evidence we have, confirming a shared birth cluster requires more than just a matching fingerprint. It demands a shared history of motion. Think of it like finding two people with identical DNA. That proves they are twins, but to prove they were born in the same specific hospital, you need their birth records, their family's travel history. For stars, that record is their orbit through the galaxy, which has been shaped by countless gravitational encounters over billions of years. Tracing their paths back to a single point of origin is an immensely difficult computational challenge. The subtle differences in their current velocities could be the result of a gentle gravitational nudge from a passing gas cloud 2 billion years ago, an event lost to time. Furthermore, stars could have formed from neighboring pockets within the same giant molecular cloud complex. They would share a very similar, but not perfectly identical, chemical makeup because the cloud itself might have had slight chemical gradients like two loaves of bread baked in the same kitchen with flour from the same bag, but one might have a touch more salt. So HD 162,826 and HD 186,302 could be true siblings from the same stellar womb, or they might be incredibly close cousins from the same stellar neighborhood. The search continues, refining the chemical analysis to include ever more trace elements and modeling the galactic tides with greater precision, hoping to find that one star whose past and present align perfectly with our own, a direct link back to the dawn of our solar system. Rewinding the galactic clock is a feat of cosmic engineering. The Gaia satellite has given us an unprecedented gift, a three-dimensional map of over 1 billion stars, complete with their precise motions. For the first time, we have a snapshot of the galaxy's grand choreography. To find our sun's birthplace, astronomers must take this snapshot and run the film in reverse, tracing the paths of the sun and its candidate siblings backwards for 4.6 billion years. This is not a simple rewind, like watching a ball roll back up a hill. It is more like trying to reconstruct the exact path of a single leaf that fell from a tree in a stormy forest years after the event. The forest is the Milky Way, a dynamic, swirling structure of stars, gas, and dark matter, all constantly moving under each other's gravitational influence. The calculations must account for the Sun's complex orbit around the galactic center, its vertical oscillation through the disk, and the gentle but persistent gravitational tugs from every massive structure it passes. The greatest challenge comes from the galaxy's spiral arms. These are not fixed structures, but rotating density waves like the patterns of light and dark in a spinning sparkler. As stars orbit, they pass in and out of these arms. The increased gravitational pull within a spiral arm can subtly alter a star's velocity, giving it a tiny gravitational kick. Over billions of years, these cumulative kicks can dramatically change a star's ultimate path. When we rewind the clock, we must guess exactly how many times our sun or a candidate star passed through an arm and how hard it was nudged each time. A slight miscalculation in these ancient interactions means our rewound paths miss each other entirely in the deep past. The result is a cloud of possibilities, not a single point. When astronomers trace back the motion of a candidate like HD 162,826, they do not get a definitive answer, they get a probability. The paths of the sun and the candidate might converge within a certain volume of space at a certain time with a 70% confidence. That is compelling, but it is not proof. It is a ghost of a convergence, a suggestion of a shared origin blurred by billions of years of galactic weather. This orbital backtracking reveals a profound truth. Even with perfect chemistry and suggestive motions, we may never achieve absolute certainty. The past is smoothed over by time, its sharp edges worn away by the relentless gravity of the galaxy. The lost siblings may forever remain strong candidates, their true family connection lingering in the realm of high probability, a beautiful and frustrating testament to the immense, forgetful scale of cosmic time. Our sun's first home was not a lonely void. It was a glittering, chaotic nursery, a place of brilliant light and deep shadow. Based on the stars we suspect are its siblings, astronomers can sketch a portrait of that lost family. It was likely not a massive, dense cluster like the Orion Nebula, where stars are packed so tightly they could disrupt each other's budding planetary systems. Instead, the evidence points to a more modest, open cluster, perhaps a loose association of a few thousand stars born from a single giant molecular cloud. Picture a celestial city, not a cramped metropolis, but a sprawling suburban neighborhood of young, hot stars, each blazing with fierce blue-white light. Within this stellar community, our sun would have been an ordinary resident, a typical yellow dwarf among its brilliant siblings. The night sky from a hypothetical planet forming around the infant sun would have been breathtaking, not a dark canvas with pinpricks of light, but a luminous tapestry. Dozens, perhaps hundreds of stars would have shone as brightly as Venus does in our current sky, casting faint shadows on the primordial landscape. The constellation patterns would change within a human lifetime as the sibling stars slowly drifted on their own paths around the cluster's center. This family bond, however, was destined to be temporary. The gravitational glue holding the cluster together was weak compared to the tidal forces of the Milky Way. Over a few 100 million years, a mere childhood in stellar terms, the gentle, relentless pull of the galaxy began to stretch the cluster apart. Close encounters between stars acted like gravitational slingshots, ejecting members into the wider galaxy. Our sun was likely one of those early exiles, gently nudged onto a path that would lead it away from its birthplace forever. The thousands of siblings scattered like dandelion seeds in a galactic wind, their trajectories diverging with each passing eon. Today, they are lost among the hundreds of billions of stars in the Milky Way's disk, their shared origin erased from the sky but forever encoded in their chemical essence. This dissolution adds a layer of profound poignancy to the search. We are not just hunting for a twin, we are trying to reconstruct a shattered family portrait, to find the scattered children of a cloud that ceased to exist before multicellular life arose on Earth. The very fact that we are here on a stable planet in a quiet stellar neighborhood might be a direct result of that early exile, a gift of solitude granted by our departure from the crowded, dangerous stellar city of our birth. The name Nemesis was not chosen lightly. In ancient Greek mythology, Nemesis was the goddess of retribution, the divine force who brought balance by enacting punishment upon those guilty of arrogance or excessive pride. She represented an inescapable cosmic justice, a force that returned with inevitable timing to restore order. For the scientists who proposed the hypothesis, the parallel was chillingly perfect. A distant, unseen celestial body that returns on a vast, predictable schedule to deliver cataclysmic punishment to life on Earth fits the archetype of that ancient goddess almost exactly. It is a myth reborn in astrophysics where the hubris is not of kings or heroes, but perhaps of life itself, flourishing in a fragile bubble only to be reminded of its cosmic vulnerability by a dark, orbiting judge. This connection between myth and modern science reveals something profound about how we process existential threats. The idea of a periodic, world-altering force from the heavens is not unique to Greek mythology or 20th century astronomy. It is a thread woven through human storytelling across cultures and epochs. Many mythologies speak of great floods, fires from the sky, or cycles of destruction and renewal, often tied to celestial signs or the displeasure of the gods. The concept resonates because it externalizes our deepest fears, giving a face and a name to the random, terrifying possibility of annihilation. In modern media, this archetype has evolved into a staple of science fiction and apocalyptic narratives. From the Death Stars of space operas to the rogue planets and comet showers of disaster films, the notion of a scheduled cosmic reckoning taps into a primal anxiety. It transforms the impersonal mechanics of orbital dynamics and impact physics into a story, a narrative with a potential antagonist, however mindless. This cultural echo makes the Nemesis hypothesis uniquely gripping. It is not just a dry scientific proposal about orbital perturbations. It is a myth for the scientific age, a story that bridges the cold equations of celestial mechanics with the ancient human need to find pattern, meaning, and even agency in the chaos of the cosmos. The search for the sun's twin, or its dark companion, is therefore more than an astronomical puzzle. It is a quest that lives in the space where data meets legend, where the telescope's gaze intersects with the oldest stories we tell about our place in a dangerous and beautiful universe. This cosmic silence is one of astronomy's greatest enigmas, the Fermi paradox. The universe is unimaginably vast and old, with billions of planets that could harbor life. So where is everyone? Why have we heard nothing, seen no signs of galactic empires? One chilling answer is known as the dark forest theory. It proposes that the cosmos is not a quiet library, but a dark and dangerous woodland. In such a forest, any creature that reveals its location, by making a sound, by lighting a fire, risks attracting the attention of hidden predators. The safest strategy is absolute silence, to hide and never, ever broadcast your existence. In this cosmic view, advanced civilizations do not announce themselves because to do so is to invite annihilation from an older, more powerful, or simply paranoid neighbor. It is a universe of preemptive strikes and existential caution. Now, consider what a phenomenon like Nemesis or a similar periodic bombardment would mean within such a grim framework. It could act as a natural, recurring great filter. This is a hypothesized event or barrier so severe that it prevents life from advancing to the stage of interstellar communication or travel. A comet shower of global extinction magnitude, arriving every 26 million years, would be a perfect candidate. It would be a celestial reset button pressed with grim regularity. Just as a civilization begins to reach for the stars, developing radio telescopes and perhaps their first tentative signals, the sky fills with fire. Their technological progress, their entire biological history, is wiped clean. The planet is sterilized or thrown back into a primordial state, and the evolutionary clock starts over from near zero. This cycle could repeat across the galaxy, on any world orbiting a star with a dark companion or caught in a similar gravitational rhythm. Life might arise commonly, even intelligence might spark repeatedly, but it never gets a sustained chance to flourish and fill the silence. The dark forest is quiet not because no one is there, but because everyone who makes a sound is systematically, naturally erased. Our own survival through one of these cycles, allowing us to reach this point of curiosity and technological ability, might then be a breathtakingly rare piece of luck. We are not hearing from other civilizations because, statistically, almost none survived their local version of the cosmic clock long enough to say hello. The silence of the cosmos might not last forever. Our tools for listening, for seeing into the dark, are about to leap forward in a way that could rewrite this entire mystery. The next decade will see the arrival of observatories so powerful they will scan the sky with a depth and breadth we can barely comprehend. Their primary mission is to map the structure of the universe and unravel dark energy. But in doing so, they will also conduct the most sensitive search yet for the ghosts in our own backyard. The Vera C. Rubin Observatory, currently under construction in Chile, is a paradigm-shifting instrument. Its core is the Legacy Survey of Space and Time, a 10-year project that will image the entire visible southern sky every few nights. This is not a static picture, it is a movie of the cosmos. By comparing these images night after night, year after year, the survey will detect anything that moves or changes brightness. This relentless stare is the perfect tool for finding extremely faint, slow-moving objects in the outer solar system. A distant, cold world like Planet 9, or a dim brown dwarf like a potential Nemesis, would betray its presence by its motion against the backdrop of fixed stars over weeks and months. Rubin's immense mirror and giant camera will see objects thousands of times fainter than previous all-sky surveys, probing the twilight realm between planets and stars with unprecedented sensitivity. It will likely catalog millions of new solar system objects, and within that avalanche of data, the subtle, telltale gravitational signature of a large, hidden perturber could finally emerge. Following closely is the Nancy Grace Roman Space Telescope, NAS, a next great observatory. While Hubble peers deeply at small patches of sky, Roman is designed for extraordinarily wide-field views in infrared light. Infrared is the key to seeing the coldest objects, those that emit no visible light but glow faintly with leftover heat. Roman surveys will complement Rubin's optical search by hunting for the thermal signatures of these elusive bodies. Imagine Rubin spotting a faint dot moving in the dark, and Roman confirming it is not a distant hot star, but a nearby frigid world, its heat signature matching predictions for a super-Earth or a failed star. Together, these telescopes will turn the outer solar system from a theoretical sketch into a richly detailed map, potentially pinpointing the gravitational source behind the strange orbits we already see. Beyond the hunt for dark companions, the search for the Sun's true siblings will also enter a new golden age. The same spectroscopic surveys that identified candidates like HD 162,826 are evolving. Upcoming instruments on giant ground-based telescopes, like the Mauna Kea Spectroscopic Explorer, will not study thousands of stars but millions. They will collect the chemical DNA of vast swaths of the Milky Way, creating a genealogical database of staggering scale. By comparing the Sun's precise elemental abundance to this massive library, astronomers hope to find not just one or two close matches, but perhaps dozens of stars from the original birth cluster. Finding a larger family would allow us to statistically reconstruct the cluster's size, its location, and even trace how its members scattered over time. It would turn a story of loss into one of reconnection, piecing together a family portrait 4.6 billion years in the making. The answers to our oldest celestial questions are no longer purely in the past. They are waiting in the data streams of the future, in the next generation of eyes we are building to pierce the dark. The overwhelming majority of stars like our Sun are not alone. In the grand census of the galaxy, binary or even triple star systems are the rule, not the exception. For Sun-like stars, the statistics are startling. More than half, and perhaps as many as 2 out of every 3, have at least one stellar companion. They dance in gravitational embrace, sharing their light and shaping the orbits of their planets. This simple fact reframes our entire search. We have been asking, does the Sun have a twin? The more profound astronomical question might be, why is our Sun single at all? Our quiet, solitary star system, with its neatly spaced planets orbiting a single central fire, could be the true cosmic rarity. This statistical reality forces us to re-examine the early solar system not as a peaceful nursery, but as a potentially chaotic environment where a sibling star might have been present, only to be violently evicted. One compelling theory involves a gravitational robbery in the crowded stellar neighborhood of the Sun's birth cluster. In those first few million years, stars would have been passing relatively close to one another. A particularly close encounter with a more massive interloper could have acted like a cosmic hijacking. The gravitational pull from this passing star could have been strong enough to sever the bond between the Sun and its hypothetical twin, capturing the sibling or flinging it away on a trajectory into the interstellar void. This event would have happened incredibly early, before planets finished forming, leaving our solar system to develop in newfound solitude. If this dramatic theft occurred, it makes the search for that lost twin exponentially harder. A star ejected from the cluster entirely, sent on a high-velocity escape path, would now be lost among the countless rogue stars drifting between the galaxies, untethered to any solar system. It would be a true orphan, its origin story erased by a single, ancient gravitational tug. This possibility adds a layer of poignant drama to the statistical odds. Our solar system's peaceful stability might be the direct result of a traumatic loss, a stellar divorce that left us alone but safe, our potential twin consigned to an eternal, dark exile. Gravity writes its signature in the orbits of everything it touches. While we search the skies for a hidden star closer to home, the architecture of our own solar system whispers of unseen sculptors. Beyond Neptune lies a ring of icy debris known as the Kuiper Belt, home to dwarf planets like Pluto. Astronomers expected this belt to be a smoothly fading disk of material, with smaller objects becoming more numerous the farther out you look. But observations reveal something startling, a sharp boundary. At about 50 astronomical units from the Sun, the population of Kuiper Belt objects doesn't gradually thin out, it plummets. This sudden edge is called the Kuiper Cliff. It's as if you were walking along a beach where the sand simply stops at a perfectly straight line, dropping off into an abyss. In the natural, gentle dissipation of a debris disk, such a clean, hard edge is profoundly unusual. It suggests something is actively maintaining that boundary, shepherding material inward or clearing it out beyond that point. One compelling explanation is the gravitational influence of a substantial, unseen world. A distant planet, perhaps several times Earth's mass on a tilted orbit, could gravitationally sculpt that edge over billions of years, its persistent tug preventing icy objects from accumulating or staying in stable orbits beyond a certain distance. The Kuiper Cliff stands as a silent monument, a potential fingerprint in ice and rock left by a hidden architect. Further in, even our human-made explorers have felt phantom tugs. The Pioneer 10 and 11 spacecraft, launched in the 1970s, were the first human-built objects to travel beyond the major planets. As they sped toward interstellar space, scientists tracking their trajectories noticed a tiny, persistent anomaly. Both probes were slowing down slightly more than predicted by the gravitational pull of all known objects in the solar system. This minuscule deceleration, dubbed the Pioneer anomaly, sparked intense speculation. Could it be the gentle drag from an unseen mass, a dark companion subtly bending the paths of our probes? After years of meticulous analysis, the most likely culprit turned out to be something far more mundane but equally fascinating: an uneven thermal radiation. Heat escaping from the spacecraft's radioactive power generators and electronics, pushing back on the probes like a faint, constant breeze. While this case was largely solved, it serves as a powerful lesson. The trajectories of spacecraft are exquisitely sensitive gravitational probes. A deviation of a few millimeters per second per year over a decade can point to a missing piece in our map of mass in the solar system. The Voyager probes, now in interstellar space, are still being tracked with incredible precision. Any unexpected wobble in their paths could, in theory, signal the gravity of something we have not yet seen. These anomalies, whether explained or enduring, teach us to read the subtle language of motion. Every unexpected curve in a path, every sharp edge in a ring of debris, is a clue written in the invisible hand of gravity, hinting at the possibility of shadows moving in the dark. The universe is filled with a ghost we cannot see. For every galaxy, every star, every planet made of ordinary matter, there is 5 times more mass in the form of an invisible, mysterious substance we call dark matter. It does not emit, absorb, or reflect light, yet its gravitational pull is the cosmic glue holding galaxies together. Now, some scientists have asked a wild question. What if this unseen ghost is not just a background presence, but an active player in our solar system's story? Could dark matter itself be the hidden hand that stirs the cometary storm? This idea pushes the boundaries of speculation, but it emerges from a real puzzle. We know dark matter exists in a vast, diffuse halo enveloping the Milky Way, but some theoretical models suggest it might also be concentrated in unexpected ways. One provocative theory proposes the existence of a thin, dense disk of dark matter lying along the mid-plane of our galaxy's bright disk of stars. Think of it as a shadow disk, an invisible layer of concentrated gravity sandwiched within the visible one. As our solar system bobs up and down on its vertical journey through the galaxy, it would periodically plunge through this hypothetical dark disk. Each passage would be an encounter with a region of significantly stronger gravitational pull. This increased gravity could act as a periodic squeeze on the Oort cloud, a rhythmic nudge from the unseen universe that dislodges comets on a schedule. Another, even more exotic idea suggests dark matter could form dense knots or streams, ancient debris from the formation of the galactic halo. Our solar system's orbit might carry us through one of these invisible rivers every 26 million years. The gravitational effect would be similar, a temporary but significant perturbation from a concentration of mass we cannot see with any telescope. It is a fringe hypothesis, to be sure, because we still understand so little about dark matter's true nature. We do not know if it can form such structures or how it interacts with itself. Yet the allure is undeniable. It replaces the search for a single dark star with the influence of the universe's most abundant, most mysterious ingredient. The cosmic clockwork would not be driven by a sibling or a planet, but by the hidden architecture of reality itself, a reminder that the greatest forces shaping our fate may be the ones forever beyond our sight. Whether the dark companion is real or not, its story reshapes our cosmic perspective. If the Nemesis hypothesis is true, then the tapestry of life on Earth is woven against a backdrop of celestial violence. Our evolution, the rise and fall of every species, would have unfolded not in a serene, stable garden, but in a shooting gallery with a clockwork schedule. The dinosaurs, the mammoths, the countless forms lost to deep time may not have been victims of random chance, but of a predictable, recurring astronomical event. This adds a profound layer of fragility to our existence. Our civilization, our art, our science, all of it exists in the quiet interval between ticks of a cosmic metronome. It suggests that resilience in the universe might not be about avoiding catastrophe, but about surviving the periodic storms long enough to rebuild. The very fact that we are here contemplating this idea is a testament to life's tenacity in the face of what might be a built-in cosmic reset. Yet, if the hypothesis is false, the search is far from meaningless. The decades spent hunting for this phantom have taught us more about our solar system's dynamic history than centuries of assuming it was static and serene. We have mapped the Oort cloud in theory, understood the galactic tides, and discovered the strange orbital alignments pointing to Planet 9. We have learned that our sun is almost certainly an orphan from a scattered family, and we have begun to find its possible siblings through chemical archaeology. This quest forces us to abandon the comforting idea of cosmic isolation. We are not a lone star adrift in an empty void. We are a member of a scattered stellar dynasty, our origins tied to a cluster of stars that have long since drifted apart across the Milky Way. Our solar system's history is one of gravitational encounters, of ejections and migrations, of a violent youth and a quieter, but still dynamic maturity. The Nemesis story, in the end, is not just about a killer star. It is a mirror. It reflects our deepest anxieties about randomness and fate in the cosmos, and our relentless drive to find patterns, to tell stories, and to understand our place in a universe that is far more connected and far more turbulent than it appears from our quiet, sunlit corner of space. The search for our sun's twin is a journey that spans the very beginning of our solar system to the outermost edges of our imagination. We have traced a path from a violent, glittering stellar nursery through the quiet dissolution of a star family scattered by galactic tides, to the haunting possibility of a dark companion whose gravitational whisper might stir ancient cycles of destruction on Earth. The evidence tells a compelling story of connection and solitude. Our sun was almost certainly not born alone, but among thousands of siblings whose chemical signatures we are only now learning to read in the light of distant stars. The grim specter of Nemesis, a Death Star on a clockwork orbit, captivated us with a mythic narrative that gave terrifying order to the fossil record cycles of extinction. Yet the cold, infrared gaze of telescopes like WISE has found no such star in the vast volumes of space where it was predicted to lurk. That specific phantom appears to be just that, a phantom. But the mystery it was invented to solve remains, pulsating with possibility. The rhythmic pulse in Earth's stone autobiography is still unexplained, and the hunt for its cause has opened richer, more profound avenues of inquiry. We now look to the galactic tide, to a hidden Planet 9, even to the dark matter that shapes the universe itself for clues to the cosmic clockwork. Simultaneously, the search for our true stellar siblings accelerates, powered by galactic archaeology and space telescopes that map the motions and chemistry of a billion suns. This dual quest for family and for mechanism reveals a fundamental truth about our place in the cosmos. We are not isolated. Our history is one of gravitational bonds, both broken and enduring. Our solar system's quiet stability may be the gift of an ancient stellar robbery, and our planet's biological saga may be written in the rhythm of celestial dances far beyond our vision. The cosmos is a tapestry of interconnected stories, and ours is still being written with every new observation, every candidate star, and every anomaly in the deep dark. So the next time you look up at the night sky, remember, you are not just looking at anonymous points of light. You are gazing at a field of potential relatives, each with its own story of birth and exile. One of those faint stars may hold the same elemental DNA as our own sun, a silent cousin from a family broken apart before Earth was even born. Which one do you think it might be? Share your thoughts and wonders